last time we were talking about the Lempel-Ziv algorithm. So what we're going to do is we're going to finish up talking about Lempel-Ziv, and then starting next class we'll talk about channel coding, which is the next major topic. I should also mention, I think we agreed that test number 1 would be over this weekend. So more details about that will be on Thursday. Okay, so remember how Lempel-Ziv compression works. Actually, there are 2 ways. The way that I presented to you is called the sliding window. The sliding window method. So basically what we have is we have a string of letters, and what we do is we find a string of letters from a source, and we will find the longest sequence of source letters such that the sequence has already occurred in the history of the source. So in other words, letters are coming in. We're remembering letters that go back over a particular window, and what we're going to do is, as letters come in, we're going to wait until the longest string has arrived that has already occurred. For each such sequence, we will record the length of such a sequence and the position in history. If there does not exist such a sequence in history, if the sequence is new, then transmit uncompressed. So if we see a new sequence that hasn't occurred before, we'll send it uncompressed. If we see a sequence that has occurred before, we'll wait until the longest such sequence is available, and we'll send, we'll basically send the index in the past of that sequence. It's called sliding window because this works over a history of k symbols, where k is some value less than infinity. So we keep k symbols in memory, and we only work over that length. So I showed you an example last time. Let's just go over a similar example quickly. So if I said k down there. I should have said, I think I used w last time for consistency. Let's keep using k. So k is 4. Then we can express the 2 rules in 2 ways. Firstly, we're going to have a flag which indicates whether the sequence has occurred before or not. So we'll say 0 if it has occurred before. If it has occurred before, then we express the length of the sequence, because remember we're waiting for the maximum length that has already occurred. Length and...
Actually, last time it was position and length.
Okay, sure. Doesn't matter, but sure, position and length. Or we will have 1 and the uncompressed sequence. source is, let's just remind ourselves how this works. A, B, B, A, B, B, A, B, 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 and so on. Then the first thing I look at, so this is the beginning, this is the dawn of history. So the first thing I look at has not occurred before. So I send that as 1A. The next thing I look at is B, that has not occurred before, so I send that as 1B. The third thing that occurs that has occurred before, so now we look at the longest possible sequence that has occurred before. If I go to BA, that has not occurred before, so I'll stick with just B. I have 0. The position is, let's call this 1, 2, 3, and so on. 0, position 2, and length 1. Now I'm here. A has occurred before. AB has occurred before. ABB has occurred before. But ABBA has not occurred before. So now I can compress this sequence that has occurred before. The position, starting position is 1, and length 3. And then we would have A, B, B has occurred before, but A, B, D, B has not occurred before. So this would be 0 has occurred before, position. Now, my window is 4, so I can only look back 4 positions. So I have to look here. The position is 4, and the length is 3, and so on. So this is basically how we would compress. And we went over this complete example last time. So the question is this algorithm optimal? Does it achieve entropy for any arbitrary source? And the answer is yes. Lempel-Ziv asymptotically can achieve the entropy of any what's called ergodic source. An ergodic source is a source where the technical definition is that the ensemble average is equal to the time average. So over time, you will see all of the possible behaviors. You'll see all of the possible behaviors of the source. So in other words, the source isn't stuck at some value for a long time. Yes?
I'm sorry. The position, do we reference it within the window or from the very beginning of the string?
So the way I've done it here is from the beginning, but it would actually make more sense to reference it within the window. So
otherwise, you have to keep the history.
That's right. Yes. That's right. So yeah, that's. In any case, this is just an example, so don't concern yourself with that too much. So, it turns out that the proof of that statement, that Lempel-Ziv actually does achieve the entropy of an ergodic source, is quite hard. What we're going to do instead is we're going to define a compression algorithm that is similar to Lempel-Ziv, but that is easier to analyze.